Hey, welcome back to discussion 16. We're looking at problem 15 on page 300. Okay, we are given three masses. We're given three masses on a two-dimensional plane, right? And so I've just taken some time to draw it out here. Let's go ahead and give these some color, right? So this is one mass at 1 meter on the x-axis, 3 kilograms. This one here is 1 kilogram. Okay, and this one here is 2 kilograms. So this is what we're given. We're told that this this angle here between these is 60 degrees. Actually, how we're given that information is we're told that it's an equilateral triangle, right? So that means that it's 60 degrees in each angle. So we want to figure out what is the height here. We're going to need to know that information. What is this height? So in order to do that, we split this in half, right? So we can say, okay, we know that there's a 60-degree angle here. So now that means that this is going to be 30 degrees, right? Because we just split it in half. Each angle, if it's an equilateral triangle, is going to be 60 degrees. If we split it in half, this is 30. Not that we necessarily needed to do that, but it is helpful. So now we can go, well, this is going to be your y, so that's going to be r. So also, I should mention that each side of the equilateral triangle is 1 meter, so that's useful as well. So now we have, to find this height, all we have to do is y equals, because we'll just call this y equals r sine theta, right? Where theta is 60 degrees. So that's just 1 times sine 60, which is going to be square root of 3 over 2. That's the value of this. This height here is square root of 3 over 2. Okay, so really the whole point of this, if you have taken the time to read the problem beforehand, you'll know that it's asking us to find the center of mass for this system, right? So I'm just trying to lay out some things that are going to be useful in the process. So the center of mass, well, let's do the y first since we're already working on the y values. It's going to be the mass, right? We have the sum of the masses times their position. We'll call this in the y direction since we're doing the y, over the total mass, right? So that means that we have, let's just slog through it. So we have 1 kilogram times 0. 1 kilogram times 0 is the position. We don't need that. Then we have 2 kilograms times square root of 3 over 2. Okay, put this, let's just do it this way because we're going to need to total the mass. And then we have, what was it, 3 kilograms times 0, again, in the y direction. Okay, and then we need the total mass in the bottom, so that's going to give us, what do we have, 356 kilograms. So that means that we have square root of 3 over 6 meters. Remember, because this is kilograms, meters over kilograms, so this is just going to leave us with meters. Okay. All right, so that's the center of mass in the y direction. All I'm doing is I'm using this formula, so you just sum these up, right? You take the mass times the position in whatever direction you're given. And since this is a two-dimensional problem, I'm doing in the y direction and the x direction. So now let's go with the x direction. So mass times x direction over total mass, right? And so we have 1 kilogram times 0 for the first one. The next one is going to be 3 kilograms times 1 meter. 3 kilograms times 1 meter. Next one is going to be 2 kilograms times, this is a half meter here, because this is halfway. Since it's equilateral, this is halfway between these two things. So half meter times 2 kilograms. So it was 2 kilograms times 1/2 meter. This is all over 6 kilograms. So that equals, what do we have? This is 0. It's 3 plus 1, so it's 4 over 6 meters, which gives you about 0.6 meters. Okay, so that's it. That's where your center of mass is going to be. So we had, it was 0.87 meters and 0.6 meters. Sorry, this is wrong. This is actually not 0.87. That was the height. Square root of 3 over 2 ends up being 0.87. That's why I got confused. This is actually, if you put this into a calculator, you actually get 0.28. We'll call it 0.29 meters. Okay, so that's what we have. 0.29 and 0.6. So let's see. If this is 1 meter up here, 1, 2, so we had 0.29, so it's going to be about here. So it's going to be about here for in the y direction, and then 0.6 is going to be about here in the x direction. So your center of mass is going to be right about here. So that's where it is. I suppose we should write this in vector form, just to be safe, right? So we'll call this r center of mass vector is equal to 0.2, let's do this, 0.6 meters in the x hat direction plus 0.29 meters in the y hat direction. Okay. You can also find the magnitude, which is something I have done, and that turns out to be about 19 over square root of 19 over 6. There's more to it than that. I'm just skipping a couple steps to save time, and this gives you a value of about 0.73 meters. That's just the magnitude of the center of mass. So what that means is here. That's this value here. This is 0.73 meters. Was it 7.3? 7.3. Yep, that's right. So we're not asked to find that specifically, but I did it for fun. So this is what you're asked to find. Okay, next problem. Number 30. We're asked, well, we're given 4 particles. 1, 2, 3, 4. Along with some velocity. So let me just double check what I'm doing here. Oh, billiard balls. That's what they are. So okay, so now I know what I'm doing. So this is 1, 3. So I wrote these numbers down for the billiard balls, right? And this is the cue ball. And so we're given these balls, and we have some velocities for each. We are asked to find the total momentum after the collision. So it's going to look something like this, right? So we have the 4 balls going in almost opposite directions. So it's probably going to be a pretty small number. Okay, but let's figure it out. So total momentum is what we're asked to find, P total. And if you look in the book in the summary for this chapter, I think this is chapter 10. Yeah. It shows you that you have the sum of the mass times the velocity of each particle. And this is also known as the center of mass momentum. Center of mass of the system, right? And also, we're given this information that each ball weighs exactly the same. So that will be helpful for us. So let's find the momentum for each ball after the collision and sum that all up, because that's what we're asked to find. So momentum of the cue ball. Okay, we're given these informations in the diagram. So we're given half, let's do it this way, half meter per second in the negative x hat direction times the mass, right? So that's the velocity times the mass. Okay, let's see, that's 1, and we're going to need that. We're going to need m ball 1, velocity 1 is equal to, well, let's do 6 first. Ball number 6, which is here. So that's a little easier. So now we have, what is it? 0.16 kilograms times 0.25 meters per second in the negative y hat direction. So those two are the most straightforward, right? This is just going in the negative x hat direction, and this is just going in the negative y hat direction. Now I just drew a horizontal for these. We're told that this one is traveling 0.35 meters per second with 60 degrees above the horizontal. So we have two components, and the same thing for this one, we have two components. This one's positive x hat, positive y hat. This one's positive x hat, negative y hat. So let's continue writing these down. So now we have m1 v1. So ball 1, this here. So the mass is 0.16 kilograms times, we're going to have in the x direction 0.35 meters per second times cosine 60. Cosine 60 is 1/2, right? That's x direction, and then negative, remember, because this is going in the negative y hat direction, 0.35 meters per second. Sine 60 is going to be square root of 3 over 2. And this is in the y hat direction. Oops. Y hat direction. There we go. Like that. Okay, next one. M ball number 3, velocity 3, equals 0.16 kilograms times, what are we told? 0.45. Here, we'll just write this out. The magnitude is going to be the same. I don't need to write it out a bunch. So this is going to be in the positive x hat direction. Cosine 30 is actually going to be square root of 3 over 2, x hat direction. And then negative y direction, sine 30 is going to be 1/2. And then literally all we need to do after we've set all this up is just add up all of our components. So let's do that. So let's sum everything up in the x direction. Okay, this is going to be, this is x. Then we have an x here. Let's go here. Let's do this x. This is actually a negative x hat, so don't forget that. All right, 0.5, negative 0.5 times well, everything is times 0.16, so we'll just do that at the end. So negative 0.5 times plus 0.35 over 2 plus 0.45 times square root of 3 over 2. This is all in the x direction, and we need to make sure we multiply it times the mass, right? So this is all x hat. We'll say that this is equal to the momentum in the x direction. Now, do the same thing for y. I mean, not sure if this is totally necessary, but why not? Why not? Okay, so now we have 0.16 kilograms times negative 0.25. Where are we here? Minus 0.35 times square root of 3 over 2. Minus 1/2. Oops, 45 over half. Hang on. I see. This should be positive. And yeah, we're good. So that's what we need. Okay. So definitely double check if you're just following along, trying to get to the answers on the homework. Definitely double check the answers here. Okay. So what did we have here? We have, this is your y hat. This is your x hat. Okay. So now we just plug this into a calculator and see what we get. Alright, so this is going to be, so total momentum is going to be 0.0135, it's very small, kilograms, meters per second in the x hat direction plus, well, minus 0.0275 kilograms, meters per second in the y hat direction. Okay, and then we take the components, square them under a square root to see what is our magnitude. That gives us 0.02938, or we could just say it's 0.03 kilograms meters per second. That's your magnitude, the magnitude of your momentum vector. So this is your total momentum vector, and this is the magnitude of the total momentum vector. And what I like to do is just look at this and see if this makes sense. And before I even started the calculation, I had sort of estimated that this would be pretty close to 0. I mean, this is a really small number. Because the cue ball comes in, smacks the other 3 balls, and then they all just kind of shoot off in almost completely opposite directions. Almost. So it's not exactly 0, but it is very close, and that's what we got. Okay, problem 65 on page 304. We're given a racquetball with a mass. It's moving horizontally in the positive x direction, and it's hit with a racket. So we have a racquetball. It's traveling this way. And then, I don't know if this looks like a, yeah, there we go. That's pretty nice. Then we have a racket. And this thing is going to strike this. That's, you know, we have, I don't know, I think a racket has like webs. I don't play racquetball, but get some tape on here. Okay, so this thing is going to hit this ball, and then the ball, racquetball, is going to move back in the opposite direction with an angle of 30 degrees above the horizontal. So what that means is that this thing is going to come backwards pretty much almost the same direction. Let's go like here. So after the collision, it comes up this way. This is 30 degrees. It's traveling in that direction. This is just to indicate the horizontal. So that's what we end up with. This is, what was it, 65, I believe? Yeah. Okay, and then so it wants us to find what is the average vector force exerted on the racquetball? I'm sorry. What is the average vector force exerted on the racket by the ball if they are in contact for 2.5 milliseconds? Okay. Well, let's just list everything that we're given in the problem before we move on. So it's 43 grams is equal to 0.043 kilograms. We're told that velocity, the magnitude of the velocity, is 50 meters per second. That's super fast. And we're told that the elapsed time is 2.5 milliseconds. Which is also, here, I'm going to need some room here. Let's move this up. 2.5 milliseconds is, if you think of a millimeter, it's 1/1000th, right? So that's going to go back 3 decimal places. So 0.002 seconds. We also know that this is going to have some velocity in, it's going to have velocity in the positive y hat direction and the negative x hat direction after the collision, and that the angle is 30 degrees. Okay, that's plenty of information to work with. So since we're asked to find an average force, it would be helpful to consider the momenta before and after the collision. So let's do that. So let's draw something a little more clear. So here's the ball. traveling in the positive x-hat direction. The initial velocity was 30 meters per second, right? And this is 50 meters per second. So let's move this down here. So now we have the ball is up here. This is 30 degrees. I mean, that's close. Okay, 30 degrees that way, 50 meters per second, right? This is 30 meters per second. The ball itself weighs 0.043 kilograms. So now momentum in the initial is mass 0.043 kilograms times 30 meters per second in the x-hat direction. Okay, momentum final is going to equal 0.043 kilograms times, well, we're going to have a negative x-hat direction, so it's going to be negative 50 meters per second. Cosine 30 is square root of 3 over 2. And then it's positive y direction, right? Because this is coming back this way. Negative x-hat direction, positive y direction. Okay, positive y-hat direction, 50 meters per second. Sine 30 is 1/2. So let's... I need room for my vectors. X-hat, y-hat. Okay. Alright, so just doing a little bit of simplifying. By the way, I'm using what is known as conservation of momentum. Actually, no, we're not going to need that in this one. I'll show you what we're going to do. We're going to do an average change in momentum. So, but I just want to simplify a little bit. So this is the same. This isn't really changing. Can't really do much with this. Okay, this one, we can just make it look a little better. 0.043 kilograms. We have 50 over 2 on both, and that just gives us 25 meters per second. Right? That means that we have square root of 3 x-hat, excuse me, plus 1 y-hat. And it's in the negative x-hat direction. Okay, cool. So now let's think about this. Let's say we want the average force vector. Well, what is a force? A force is, it's a mass times acceleration vector, right? That's going to be, we'll call this average. That's going to be a mass times the change in velocity vector with respect to time, right? We'll call that average as well. We can also think of this as just the average change in momentum, or delta p, right? So delta p, where p is mv. And so this is going to be, if we write it like this, dp dt, this is average, right? This is going to give us, since we're talking about averages, this is going to give us delta p, change in momentum, over the change in time. So let's use that, because we have all of the information we need to solve this. So that gives us, so now let's go back here. Average force vector equals d delta p over delta t. This is going to be p final minus p initial over time final minus time initial. And so let's just, let's do this. We have vectors, right? So we actually need to consider these as vectors. And then what do we got? P final. So in the x-hat direction, we have, let's pull out 0.043 kilograms, because that's common to everything. And then this is going to be, what was it? It was 0.0025 seconds. Okay, that's common to everything. And then so now we have just final x-hat minus initial x-hat. And that's going to give us what? Negative square root of 3 minus, what do we have here? Excuse me. Minus 25 times square root of 3 minus 30. Okay, this is your x-hat direction. All right, and now let's make that look a little better. And now we have final y-hat direction minus the initial y-hat direction, but we have no initial y-hat direction, so that's just going to be the final y-hat direction, which gives us 25 meters per second y-hat direction. So we can plug this in and see what we get for each component. That's going to give us, we'll call this here negative 1.26 times 10 to the 3 newtons in the x-hat direction, plus 4.3 times 10 to the 2 newtons in the y-hat direction. That's the average force. Problem number 40 on page 302. Okay, we're given a setup where we have 2 carts that are on a horizontal table, and we have a spring. They're both pushed against a spring this way, so the spring is compressed and it's going to be released, and they're going to go sailing off in opposite directions. Part A says, what is the net external force on the 2-cart spring system? Well, what's included in our system, it actually tells us in the problem, a 2-cart spring system. That's it. That's our system. What's included? The carts and the spring. Why aren't we including gravity? Well, it doesn't really apply here. I mean, we're not going to have, if this is frictionless, we are told that rolling friction is negligible, so we don't really need to consider that. So that means that there's no frictional forces that we need to consider. The gravitational force is just going to balance with the normal force. So really, we only need to consider the force in the x-hat direction. So long story short, there are no external forces on this system. Next, it wants us to find a velocity for cart 2. Cart 2 is actually over here. This is M2, this is M1. And so we can use conservation of momentum to do this. What is the initial momentum of the carts? Well, we have M1, let's go M2 V2 plus M1 V1 is equal to M2, we'll do it this way. We'll just call it initial, and then M2 V2 plus M1 V1, and then this is final, right? Okay, so now at the very beginning, we can just say we're just going to consider what the momentum is just before it's released, and that's going to be 0 for both carts. These things are just sitting here stationary at the moment just before release. Okay, so this goes away and is equal to 0. So that means that we end up with, okay, so let's say M2 V2 is equal to negative M1 V1. And these are both in the x-hat direction, right? So now, what did it want? It wants velocity of cart 2, so V2 is equal to negative M1 V1 over M2 x-hat. There you go. There we go, like that. So that's your velocity. Okay, so now C. Part C suggests that we've made a mistake in our laboratory setup, which, wow, okay. But here we go. So let's take this down here. Copy. We're going to paste this over here. So now here's our laboratory setup, and it's telling us that we've made some error. And instead of having a level table, we now have an unlevel table. It says in this situation, what changes in parts A and B if the track is not level as shown in the figure? Well, now, okay, so recall that we defined our system to be a 2-cart spring system. So we just had the 2 carts and the spring, and that was our system. And we had no external forces operating on our system. Everything was just fine. But now if we've accidentally tilted this thing up, and this is wildly exaggerated, by the way. I mean, you could have, this thing could be tilted just slightly. Like if you're in the lab, I mean, you would notice that as well. It could be just like the smallest amount. Well, it won't let me do it, but you understand. So now that this is the case, now that we've made an error and we have some angle, and this isn't as perfect as we thought, so what's happening is that we have an external force acting on the system, because our system is a spring and 2 carts, recall. So now we have gravity, and gravitation is an external force because we did not include it in our initial system. So let's look at this a little closer, because I think this is rather important. So if we have our cart here, we have a cart here. There's a spring with a constant K. Okay, we have a normal force for both carts. Right, we're going to have gravitational forces pulling downwards for both carts, which we didn't really need to consider in our other system, right? These components are going to cancel. We'll call these our Y components. These Y components are going to cancel as usual with our inclined plane systems. And then we are left with something else. So what are we left with overall? A net force, right? So if we write this out mathematically, we're going to have in the x direction. Remember that our y components are going to cancel, because otherwise this thing would just be bouncing off the track, right? So we don't have anything bouncing off the track. So we only have something in the x direction. Let's see if it cancels out, or if the external force of gravity is actually affecting our system. So, well, we have a negative k x2, that's a displacement from x2, plus k x1. We have m2g sine theta, right? From our diagram here, this is m2g sine theta. And then we have also m1g sine theta. It's going to be the same theta. And this is going to be, we'll call it, we don't know if it's in equilibrium, so we're going to call it m net acceleration in the x direction, right? If in our initial setup, if these were the same, if our displacements were the same, then these would just cancel out, right? Because we just have these forces going in the opposite directions that are equal, and those would go away if they are in fact equal displacements, right? So those would go away. But now we're left with what? Now we have sine theta, g sine theta times m2 plus m1 is equal to net acceleration. So these would cancel because this is net mass, and then g sine theta is actually, that is your net acceleration. So yeah, we do have external forces acting on the system because we didn't include those in our system initially. So one thing we should consider, because it asks what changes in part A and part B, so we went through this, but also for your velocity, you're not going to be able to use conservation of momentum anymore, because that's only for if your system is conserved. There are no external forces acting on your system. So this is for a closed system. You cannot use this to find your velocity. So you would have to use your work energy theorem in order to find your velocity, right? So you'd have your initial energy plus, you can say 0, and then your final energy would be, well, I don't know if that's 0. You'd have to just calculate this to figure it out using, kinetic and potential energies as you normally would, plus your change in the internal energy overall. So that's how you would have to find your velocity. I don't think it asks, it's just conceptual. So let's move on to number 41. So number 41. It's the same problem. and you're asked to find the velocity of cart 2. So we're asked what is the net external force on the 2-cart system. It says in the problem 2-cart system. I'm assuming that they mean the same thing as that they meant in part A for number 40. What is the net external force on the 2-cart spring system? In which case there was no external force. But if they're just saying that it's a 2-cart system, then the external force would be the spring force. But I don't think that's the case here. So I'm just going to say there are none. There are no external forces. But be aware that sometimes the wording can be tricky in these problems, and I think if we were only considering the system as 2 carts, then the external force would be the spring. But frankly, if you have 2 carts compressed on a spring, you don't want to only consider the carts as part of your system. You want the spring in your system. Okay, so next, find the velocity of cart 2. Okay, well, we had this before, right? And this was negative m1 over m2 v2 in the x-hat direction. And all we have to do is plug in the values that were given. So we get negative 1.0079. What is this? Meters per second x-hat direction. Or we can say that this is closer to negative 1.01 meters per second in the x-hat direction. Thanks for watching.